Oh, okay. Hello, everyone. Let's start our keynote speech today. I'm Hong Yi Li. It's my great pleasure to introduce today's keynote speaker, Abdul Rahim Mohammed. He was a research scientist at Meta, and before he joined Meta, he was a principal scientist of Amazon and a researcher at Microsoft. And he is my research hero. He was part of the team that started the deep learning revolution for speech processing in 2009. And his publication has more than 40,000 citations now. And he is the pioneer of self-supervised representation learning. He's truly leading the progress of this field. His team invent lots of very well-known and widely used self-supervised speech model, including Huber and WebDirect 2.0. And he is an important member of the team invented Superb, the evaluation benchmark of self-supervised representation learning. And his research opened the possibility of textless natural language processing. This start a new era for spoken language understanding. I really look forward to the talk today. So please join me to welcome our keynote speaker.
Well, thanks, Hangi, for your kind words. I hope that I deserve them. And again, thanks for the organizing committee for the amazing gathering and for the great organization and for inviting me here. And for all the attendance for this kind of nice and warm environment that we have enjoyed yesterday, and hope it will keep going with us for the rest of the conference. So yeah, as Hangi mentioned, I used to work at Meta, and just recently in December, I decided to work with a bunch of colleagues from outside Meta and start up a new company. We are going to announce it very soon in February. But yeah, I just like prefer to leave my affiliation kind of like just like empty for now, and very soon we'll have the press release about it. So today's talk will touch upon many papers that I was involved on. I was super lucky to work with lots of brilliant scientists in the audience here and at Meta to do many of that work. So all that work, we have done it while I was at Meta. So the focus here will be around self-supervised representation learning and how this led to what we call textless NLP. So first of all, these are my goals. Like I was thinking about like making a talk, and I thought about the jet lags that I'm suffering right now, and I thought like, okay, let me make that a morning, like a nice morning talk, nothing so deep into like kind of low-level details. I will tell you why in a moment. But also, I wanted to focus on questions rather than the answers. I wanted to kind of motivate thinking, and I would love for us to have very nice back and forth in questions. I think this would be the most interesting thing for everybody, rather than my own words. So please ask questions whenever you want to. And I also wanted to connect the dots between many research ideas that we have worked on over the past many years. Rather than being kind of focused on the trenches in the low-level details, we need to go a little bit on the high level. So first of all, I wanted to kind of state the obvious. We have a revolution in generative AI, and here I'm talking about two sides, like the user generated content or creator generated content and AI generated content. And I'm starting with some quotes from Andrew Chen. He's a writer, business writer, and general partner at Andreessen Horowitz, one of the very famous VCs in the US. He wrote a LinkedIn post around the same time when ChatGPT went public. So he was thinking, he is contrasting user-generated content, which defined the past decade. So if you think about, like, YouTube, Facebook, Twitter, etc., TikTok, etc., all these companies are organizing, monetizing user-generated content. And he thinks that the next decade will be shaped more by the AI-generated content, because the AI-generated content will not just be about the users, but also about we are what the creators now are offering us. We will be able to generate that through AI. So again, not necessarily totally by AI, but it's more like, through an interaction with creators. So think about Netflix, think about Amazon videos, think about, gaming companies. How fast and what will be the cost of generating the new game if you have an engine that generates the music for you, that generates some of the images for you. So if an artist need to work on some piece of of that game for 3 weeks, the artist he or she can do that, say, in few hours now by interacting with a generative AI system. So now this can reduce the cost dramatically, reduce the time dramatically. And he is asking the question, like, how this can redefines the entertainment industry, for example, and many aspects of our life. So thinking with that in mind, of course, I thought that it would be always fun to have a slide generated by ChatGPT. So I just logged into my account with ChatGPT and I asked ChatGPT, give me a slide about advances in generative AI, and I got a very coherent and nice slide like this. So you can imagine, like, very soon people will start using this for writing essays, using it for writing books. It will be interactive, so it will cut the time and cost of generating ideas. I'm not expecting ChatGPT to have a very nice philosophical discussions with us, but at least it will help us to fill in the gaps. We can provide the skeleton, it will fill in the gaps, and we'll keep refining back and forth. And it will cut the time to have all that dramatically. So this is for the text side, but in the image side and the video side, we have tons of innovation in the video generation, in the image generation, in the music generation. And not only in this area, we have worked also in the text NLP project to generate conditional and unconditional speech. And there has been amazing work as well from other labs, from Google, and also for AudioGen, when you can not only generate speech, but you can generate non-lexical sounds, like, whistling or wind blowing, etc., within context. So these are been all very, very interesting. But below the surface, what enabled this revolution to happen? So now, again, like, this is the overarching idea. We have AI generated content. It can make a revolution in business. It can make a revolution in how people interact with digital platforms. But now, getting a little bit lower and thinking about, like, what enabled this revolution, in my humble opinion, of course, like, we have amazing innovation and hard work of AI scientists and engineers. But also we have great help from data and compute. We have scalability. We have spending on that that's growing heavily. We have platforms like Hugging Face, for example, that's democratizing the field and offering the trained models publicly to kind of shortcut the kind of, like, to speed up the cycle of engineers that might not necessarily have access to the model or might not have the skills to start interacting directly with the model, is offering APIs that people can work with it very, very quickly using their backend serving the model. So again, this cut the time for people to run and work with these models a ton. Another one, of course, that I cannot ignore here are the different generative losses that enabled us to have these amazing generations, like predictive losses for language primarily, adversarial and diffusion losses for speech and for vision. But the main topic of this talk will focus on the fourth pillar, I believe. Again, this is not meant to be a comprehensive list, by the way. So I might be like, of course, might be missing other factors, but the main one that I wanted to talk about today is high fidelity representation learning, because once we have high quality representations from language, for example, I can hook it to a diffusion model and generate images, for example, or a speech that is kind of drawing what I'm writing in that text. So having these high fidelity representations are very important for us to keep going with this AI generated content. And this is why I believe this is kind of central to this revolution in generative AI that is happening. And we are talking about self-supervised representation learning. I am not going to jump into low-level details because with amazing partners here and in the community, we have delivered this tutorial last year multiple times at ICASP, IntraSpeech, and eMNLB about self-supervised representation learning for speech processing. And the materials for this tutorial is available online. You find the recordings, you find the slides. We talked about the low-level details of multiple self-supervised techniques focusing on contrastive approaches, predictive approaches, generative approaches, and we covered a wide range of these techniques that was developed that were developed over the past many years. So I will kind of not jump into the low-level details. If you are excited about some of these details and want to ask questions, please feel free to get me on the rest of the day. We can chat about any of them, but in this talk, I will return back to focus on the big ideas around self-supervised representation learning. So one thing that I'm thinking always about is like the main reason, one of the goals of representation learning is for us to take the approaches and systems to be closer to how we as humans interact with data. So for example, early systems for speech recognition were supervised systems where we need to have paired text and audio data. We need to prepare lexicons. Sometimes we need to prepare pronunciation dictionaries as well. For some language, like early on, people were not even learning these pronunciation models from data. They were writing them by hand, etc. So having this supervised ASR system, and then we started thinking about, okay, we have succeeded in that. Can we do unsupervised speech recognition, where like even in the early 2000s, 2002 and 1999, people was doing the unsupervised speech recognition, which is now similar to what we call semi-supervised speech recognition, where you have a model, you have unpaired text and audio, you kind of train the text to have a language model, you have audio that you kind of decode it with a teacher and use it. But now, but again, the whole power of that is to have unpaired text and audio, and still you have lexicon. And then we went a little bit closer to humans and say, okay, let's get rid of the text altogether, let's get rid of the lexicon altogether and just work with just audio. So if we have a human who's like, like again, my kids, they grow up until maybe a few years in their life, they're able to talk, interact, full humans without knowing how to read and write. So this is more human. The laughter, the interactions that they have, like how to have dialogue, is completely ingrained in their ability to generate and consume speech. It has nothing to do with the text by itself. And this is what is very important for us to build systems that mimic that. And I will refer to that in a second. Another view that I love, one of my superheroes, Jim Glass, wrote that paper back in 2012 that's called Towards Unsupervised Speech Processing, where he had that very nice graph. I think we were just like following that graph step by step. He was talking initially about expert-based systems where we were writing dictionaries and pronunciation models and kind of curating phoneme lists per language through human experts. And of course, we have parallel speech and text data. Then we started to say, like, you know what? I can learn pronunciations for this language from data. I can just give me the paired text and audio, and I will learn most of the other things from data. And this is what we call data-based systems. And then this is like the revolution like that happened later. It's called the decipher-based, where we have unpaired text and speech. And then the very last one is more like the sensor-based, where we are not now talking about a single modality. Here we talk about like multimodality. We have interaction, we have visual input, we have spoken input, etc. So it is a very, very interesting paper. Again, I thought about it when I was writing the slides, and I like these are always I call like the gems from the past. Like very, very, very interesting papers that's kind of guiding us through the way as we're thinking about developing new systems. So yeah, so in the vertical of supervised learning, supervised ASR, representation learning helped us define or redefine supervised like labels. Like when we look at the like Wave2Vec2 and Hubert, we were able to train systems on insane amount of audio data, but fine tune with 10 minutes of audio with like either like as low as 10 minutes. Of course, the graph here shows the results for 10 minutes, 1 hour, 10 hours, all the way to almost 1,000 hours of audio data. The point is that when we created the dataset Library Lite that has the 10 minutes of audio, of course, we're thinking, you know what? It will never work, but we wanted to put it there as an ambitious goal. And to our surprise, we ourselves, like, 4 months later, we were getting amazing results on the 10 minutes. Like sometimes we underestimate our systems. We underestimate our abilities to get good numbers. So I think this was a very good learning experience. Like challenging ourselves is the best thing for us to do. So we were able to get even a single digit order rate using 10 minutes of supervised data. On the second vertical of unsupervised ASR, representation learning enabled us to learn nice mapping between language as represented in characters and words and language as represented in spoken input. And just like, we have the good representations, and what you need now is to have that rotation matrix, or like just like mapping between these two representations, although they are not paired, but as our friends in machine translation did back in 2017, if I recall the year right, they were doing the same thing. You have unpaired languages, you learn the representations of them, and then you have a rotation matrix, or like, mapping between these two dictionaries, and you do it fully in an unsupervised way. What enabled us to do it here is to have that high quality representation of audio that enable that unsupervised speech recognition. And again, the results are impressive. So without any labels, with zero labels, the systems can go as low as like 6.5 or 6.3% on test other in libre speech. Again, of course, using self-training, and again, it's unpaired speech and text. So I'm using every trick in the book, of course, to get this to work well. But again, the whole idea of reaching that level of performance with zero labels is insane. Like, like thinking about that 5 years ago, it's an ambitious goal that was achieved. So again, representation learning enabled us to achieve this goal. A third pillar here, which is related to textless NLP, that representation learning enabled. And again, I wanted to go to the high level to understand, to kind of reiterate the motivations why we need to have textless NLP. It's not because we hate text, but actually because babies learn first languages through spoken interaction. And this is very intriguing how they are doing that without text. Also, limiting our abilities to use text for our systems is not inclusive to include lots of languages and dialects. Even my own dialect, Egyptian Arabic, is not written. There is no orthographic rules agreed upon between like all the speakers of the dialect to say how to write it. There is multiple ways to write multiple words in Egyptian Arabic and many other dialects and languages in the world. So having genuinely textless approach to this will just bypass this problem automatically and deal with it as humans are dealing with it. Another thing which is very interesting, even for written and high resource languages, is the whole idea of non-lexical cues, the idea of having hesitations when we are talking, laughter, interruptions. Like I might be chatting with Ahmed here, and we are interrupting each other. Like, if you are annotating this, you say, oh, interruption. But is that interruption because we are fighting for some idea? Or are we interrupting each other because we are super excited about an idea, and we are just like, saying the word that like, like we are just like saying what he is about to say. We are interrupting each other because we are super excited about the topic. So You cannot represent that with just like a rigid, annotation guideline, let alone like, the amount of effort in writing the annotation guideline by itself, let alone annotating the data. So modeling the data distribution directly is what we need to move to the next level. If we think about what's exactly the next challenge for the community, I think it is getting closer to human level of interaction, human-human interaction. And I think being textless is core at that goal. So the goal here, as I mentioned, is to set our systems free of the limitations of text and all the annotation needs and costs that are associated with them. And the other thing is that we need to match the distribution rather than matching the distribution of some cleaned set of speech and calling everything else noise. I don't like calling everything noise. I call them just like non-lexical cues. Like if I'm chatting with you on the phone and you hear sizzling sound, you would know that I'm in the kitchen cooking, for example, or doing something. I love cooking. So you will know that about me just by listening to that sound. So it is not noise, it added an information in that discussion that we have. So I think, again, having that holistic view of human-human interaction is a key for building next generation systems. So we make the very tiny step towards that, building like what we call the generative spoken language model, where we first discretize audio through self-supervised technique. So you train a system, you take the encoder, you discretize it using like, your favorite technique, could be k-means, j-mems, h-mems, whatever you like. You quantize it, and once you quantize it, now you have discrete tokens that you can deal with it as any other language. It's now pseudo language that you are learning on the fly on the data, and then you can learn a unit language model on top of it. And once you have it, you can have a unit to speech, not text to speech in this case. Like, it's fully unsupervised. You have spoken input, you run it through the encoder, you get a bunch of units. Now you learn a unit to speech system that generates for you. And once you build that system, you can generate conditionally, unconditionally. You can do lots of things. Again, you are not limited by the abilities of TTS. You can generate systems, and we did that. Where systems can, like, you have a dialogue between two people, you have two streams that you are modeling, and one of them is laughing and the other one is interrupting, and like generating such dialogue and engaging dialogue is not possible with the normal kind of annotation. Again, annotation guidelines systems that are built today for TTS. But being genuine to the data, we were able to do this in GSLM. So of course, evaluating that system by itself is another issue, because now we have an audio data that's coming at the output. You need to start thinking about evaluating. And how we thought about it, we say like, okay, let us think about how this is similar in terms of, we need the content to be novel enough. So we have a little bit of perplexity that we need it to be high. It doesn't need to be boring, but on the other side, it needs to be correct. That doesn't need to have like, random garbage that's generated. So you can read more about that in the publications we had on that topic. But one thing that we learned building these systems is it re-emphasized a very old friend, which is disentangled representations. Because if I need to generate audio, I need to have controllability. I need to generate audio of a person's identity, or a person, like I want to generate something of my voice with some emotion, with some background noise, and the content that I know. So like we need to disentangle all these factors that contribute to the speech signal so that we can have controllable generation. So having a very good representation model that is able to do this disentanglement is a key. And one experiment to kind of validate the abilities of one of our systems on doing this disentanglement, to kind of capture the content and focus on it, was to do the symbol compression. So if you have audio, you quantize the audio through these discrete tokens learned by Hubert, for example. We have done that on using multiple other systems. Hubert just achieved slightly better results over the others, but all of them are great. So you get the representations, quantize them with simple k-means, like nothing fancy. And I remember in that figure, for example, we were using 100, like a code book size of 100. So like, again, something tiny. And once we have that, you can generate speech out of it. And you can see here that the bit rate is usually like very, very small, and the quality is just second to the uncompressed audio. So meaning that the system was very good at extracting the content and generating it. Of course, the system has the decoder, so it can generate. But also in the same paper, what we found is we can use that content to map, to do speaker conversion. So I can take the content from one speaker voice and generate it in another person's voice. And the very interesting observation here was that compared to other systems, Hubert was able to do this good disentanglement. So if I take a content from a male speaker, I want to generate it through a female voice. It does that very nicely, while other systems which entangles the speaker style, identity, plus the content, once you move across gender, all of a sudden you have very funny effects in the generated content. So again, like, these are things that we're looking along the way to tell us signals and hints about the quality of disentanglement through the system. However, they were not built with disentanglement in the loss function. Maybe this is what you need to do. Like, how can we really build systems that have disentanglement baked in those functions? So it might be very interesting, let alone being a nice application by itself for representation learning is to have extreme compression. And this is why I'm referring here to, there is a ton of other more recent work that focused on compression. I'm not talking about it here because it's not the topic of the talk, but there is impressive work on speech compression using representation learning that came out in 2022. So once we have that system of discretizing speech, having like, and then we kind of bring the machinery of larger scale language models, and of course bring the machinery of generative and like, hi-fi GANs and other impressive unit to speech or text speech. In this case, we are just removing the text and using units. Once we have that, now we have all the blocks that you need to do very fascinating applications. So I'm listing a bunch of the papers that the team at Meta did in 2021 and 2022, focused on expressive generation of speech modeling, how to incorporate prosody when we are modeling the sequence of speech and when we are generating it, how we are generating dialogues, playing with the style conversion, speaker conversion, emotion conversion, speech-to-speech translation, and also translating to unwritten languages. Of course, you can imagine there is a lot of other systems that could be and will be built of combinations of the above. Like, if I need to have, say, expressive translation with the same voice of the speaker that's saying it. Like now, once you have the building blocks, that should be easy to achieve. It's just like matter of doing it and perfecting it, of course, as a system. So now we have all the tools that are needed to achieve that vision of unlocking the potential. So this is great. So if we have good representations, it can help us build all these systems. However, what else we need to do other than building good representation models? So what are other needs? I always think about the ecosystem. So representation models are, can think of it as the center, but there is a lot of other systems that we need to build to have that ecosystem for representation learning so that we can build next generation, generative AI, systems and businesses. So the ecosystem, like I was thinking about, like, what we need. First of all, we need to have scenario focused benchmarks. So benchmarks are very important because once you have a benchmark, you are driving the entire industry, like academia, towards new territories and customers. And this again, like all these areas, it's kind of like, for me, it's more like call for actions. Like these are the areas where we all need to work on. If you're not necessarily working on the representation learning by itself for the next big thing in the representation learning, for whatever reason, like maybe you might not have the same insane compute that's required to build these models and being competitive with these models, but you can do bunch of, like, some or all of this, you can touch upon all these components in the ecosystem. And of course, one of the top of it is building benchmarks. And of course, one reason to build benchmarks that us as scientists and researchers, we love breaking and like, benchmarks and like being at the top of the leaderboard. So I think it's very good playing to human psychology, like, have a benchmark so that people can work more in that direction. And the other thing is that we need to design these benchmarks at the right level of abstraction, because there are lots of variations in these units, approaches, architectures, training data. So being customer focused and scenario focused in building the benchmark and the right level of abstraction is a key to that. And of course, talking about benchmarks, please don't miss the superb challenge on Thursday. So Hangi is like leading us in this area. Like he and Shinji, and like I made like the Daniel, I've met the Daniel Lee. So like, our great leaders in superb. So please don't miss that. I hope that you will enjoy it. Another sub block that I was thinking about is that the nature of these, like, units or pseudo language that we are discovering. We found that like if we have higher quality units, it makes sense that they will be better for having a second iteration of these representations. And we did good amount of effort among other researchers in other places as well. I'm just like citing one paper that recently we put in archive here, where we're looking at, once we learn the representations, we're like smoothing them out so that they are not like kind of like jumping frame by frame again. We are not using something, we're not using discretization model that is smoothing them. Maybe we can need to use like something like HMM. We use like you can think of it as an approximation to HMMs. Again, as I promised at the early on, to respect the morning lecture, I'm not going to equations and details. I would love to have that, but again, like you can have a dynamic programming approach to smooth out these units. And yeah, this like on zero speech metrics, it was providing us with good numbers. We thought like, okay, let us get these units, put them together through like, byte pair encoding, and it should help our systems. And then we tried to use that for training both encoder-only representation models and encoder-decoder representation models. So what we found was very interesting, that encoder-only representation model didn't help a lot. Like it didn't benefit a lot from having long-range, higher quality units, which was very intriguing. We still like, we didn't fully uncover the reason for that. However, having an encoder-decoder pre-training. So in this case, if you think about Hubert, you get the output, you discretize it, and then you have an encoder-decoder system that is fully trained on audio, but the target of the decoder is the discrete tokens that you learn it from the first iteration of encoder only. So this is what I mean here by encoder-decoder pre-training. So once you do that, the larger units, the long-range units help in the decoder. And we were happy when we saw that the second column here is that once you have, so 12 layers of encoder only, encoder, and then you have 6 layers of decoder, the best long-range unit was achieving good results, 15.1. And again, all these results was not using language model. We wanted to focus on the quality of the representation quality itself. So we did not involve an external text-based language model here. So just to focus on our analysis. And the results here, if I remember well, it's just like, dev other / test other. So these numbers are dev other, test other numbers. So we were so happy. Okay, now long-range units are good, but we added 6 layers of capacity to the system. So let us do the encoder only with 6 more layers. And I'm not sure if it's surprising or not. The encoder only was able to even catch up with the frame level units, which is like not necessarily smooth, not necessarily long range, not necessarily good for under zero speech metrics. So it seems like even if the units are not necessarily super good, the encoder-only systems are able to learn good representation out of them, which is still something that we do not understand. And I wanted to bring this as a question and something for us to reason about. I have no idea why this is the case, because we have other work that showed that if you have word level and you discretize or having the right boundaries of the word level system, all of a sudden you have very good representations. You can capture syntactic and semantic level information on the subsequent components of the model. So we are still not able to learn representations that are kind of tied to the language and semantics of language. So there is still missing piece. There is still something to be done on the representation learning area to disrupt all the other system, but it kind of should involve our knowledge of language and like how to drive this representation. What exactly should be done? I have no idea. But from the numbers, it seems like there is a strong case to be made that there is still some other representation model that nobody did yet that should be done in this area. So another thing that I wish that people work on and think about, I'm not sure if it will happen, but we should, which is focused around privacy preserving representation learning. We are living in like in a world where better models mean more and more data. And audio data are private data for users. And this, of course, invoke all this genuine and problem. We are users as well of like we are not only creators of technology, but users of technology as well. We appreciate people's privacy and our privacy. So we need to be aware of that, building systems that are privacy preserving. So what I was thinking about as needs in spoken language technology systems is that we need to have an ability to adapt dynamically on the edge. Like, you know, if I have Alexa or Google Home or whatever, your preferred Siri, preferred personal assistant, we need to have as more like, you know, my genuine assistant. Like if you think that I need to have that assistant listening to me 24/7, of course, this is violates my privacy because it listens to my all discussions with my kids, my wife, and so on, my friends. Of course, that conversations, I cannot pass it along to the backend server of any company. So as a user, but if I have systems that for representation learning. And we thought about, okay, can we have Hubert to be binary? And we were playing with couple techniques that was done from Amazon team, Alexa team, and actually from Alexa team, um, of like forcing the weights to be more uniform so that they are making better utilization of their quantization bits. And another technique that came from Meta, where is again doing the same goal but using slightly different technique, and we're comparing them again, showing the kind of the cost in word error rate and other metrics in Superb when we were doing this harsh quantization, again all the way down to binary activations and weights. So another thing that we thought, again, to touch upon that vision of privacy preserving and lifelong learning and user specific or household adapted systems, we released a benchmark. We call it Libre Continual, where it contains the speakers from LibriVox that recorded a lot of audio data. So now we can think of this as like kind of longitudinal users. So we have the user, of course, we have the Libre speech, which is kind of um, like not included in this data, to ensure that this data is not included in our speaker-based data. So you can think of Libre speech data as your back-end or server-side model that you train initially and you ship to a customer. Now, once you have that model to the customer or to the user, this user is using the system. So you have like maybe 10 hours or 20 hours of that user worth of data for that particular user. And you can use part of this 10 hours for training and adapting continuously as you go. And then there is 1 hour for validation, 1 hour for test for that particular user. And then rather than aggregating the order rate and reporting one number, we can report per user order rate, and we can report averaged per user order rate. So this way, I know that we have these systems at big companies, all the big companies they have who are building federated learning systems. Of course, they have the benchmark, but we don't have a similar benchmark for the community to start working on that direction. So we thought that it might be good to offer this for the community as a challenge so that we can really build systems in continual learning for speech. And as making a tiny step in that direction, we thought about building disentangled transformer models where we can have subset of components that are fixed for all users, but some other sets that are activated and adapted for other subsets of users. So if I am adapting the system for me, it will be slightly better for me than any other users. But when I have a friend visiting and interacting with my device, the results of that interaction is not terrible. It's still back off to like some reasonable quality, so which is the core quality. So you can read the paper for more details on that. Another area that, again, another block of serving the whole idea of representational learning is how to analyze these models. And back to the panel discussion that Sanjeev is going to run in tomorrow is like, do we really need to use language? Do we really need to use all this kind of old school human information, perception, production, information of human? Of course, this is not old school. This is the science that built this field. Like, the language, like, techniques come and go, but the language will always be there. Humans will always be there in our systems. So we always need to understand human production, human perception. So if can we use these views to analyze our systems? And to our surprise, we were taking representations from a representation model and using it to predict traces, the EMA traces. And again, the whole idea here is that we wanted to see how much we can benefit or predict the low dimensional manifold of audio in that production space. Like, we know that speech production has a very low dimensional representation. So we wanted to understand how can we predict it, how can we benefit from it. And to our surprise, first of all, using only 5 minutes of audio, we were able to predict these representations with reasonable accuracy. And more interesting, when we applied this for the super benchmark models, the ranking of our ability to predict was almost aligned with the system's ranking on the superb leaderboard, which was like a very, very interesting thing. That maybe the ability of the system to mimic speech production is kind of like telling us about the system's ability to perform on multiple other techniques. Again, this was some other beautiful thing to harness from try to tying analysis of human production, human speech production to our models. Another thing was the work that we did around human perception. So in this case, I would just like, you can read the paper for more details. Again, Yuaning in Iching group was again, I was super happy to collaborate with them in that work, where they have patients who are going through a surgery with their brain exposed, so they can actually probe the brain. I think like Nima gave an amazing talk yesterday, and he is our expert in the community about this this field. In that data, we had users that are not speakers of Mandarin; they are English speakers, or like American speakers speaking English, and get them to listen English sentences and Mandarin sentences. And other patients going through similar surgery in China who are not speakers of English, they never learn English in college and school, to listen to English sentences and to Mandarin sentences. And what we found was that for the first time, the systems that we are building are mimicking what the brain is doing by, so if you have the speech, English speech, and you run it through the model, and then you try to predict the brain activations at different areas of the brain. So there are areas of the brain that model the low-level acoustics. There are other areas that model the kind of a higher-level lexical information and semantic information, etc. So trying to predict the activations of the brain at different levels, as again identified by the experts in this in the field, of like which areas are responsible of this of like understanding speech at whatever level. So what we found was the system's ability to predict the low-level acoustics was okay. Like even if you train an English system or a Mandarin system, I'm here to talk about the actual self-supervised model. So it doesn't matter. You were able to predict the acoustic level very well, even if the model was not trained on that language. However, you will not be able to predict the higher level representations that are more related to lexical and semantics unless the model itself is trained on this language, which is very similar to what us as a human are doing. So like if you now, I've never learned Mandarin in my life. So if you play Mandarin to me, I can listen to it. But if you tell me anything about the lexical, I don't even remember that. I did not create any meaningful representation in my mind about that language. And this is what we found that the systems, our representation models are doing that as well. So it was a pretty fascinating observation. There are a bunch of other very interesting things in this paper about like, attention and how attention works at whatever granularity and how does it relate to the nature of the language and so on. So again, I would love to hear your feedback about this paper when you read it. But again, the long story short is that using our knowledge of human perception is giving us a lot of ideas for future directions of how can we drive these representation learning models even more. So we talked about all of that. So definitely we need your help on many areas. Of course, you can develop new techniques. As mentioned, there are always gaps in these techniques. If not, building components that help in the ecosystem of representation learning, or of course, use all of that and build ginormous models to generate the next kind of like, wow, model for generating images from speech, generating speech from speech, and so on. So it's always great to talk to you, and thanks again for your invitation. And I hope that you enjoyed the talk.
So for the excellent keynote, and are there any questions from the audience? We have around 10 minutes. Okay, here.
Good morning. Thank you for a wonderful presentation, Abdurrahman. I have a quick question related, not specifically to the speech side, but all pre-trained models in general. So as they become more and more the key building blocks for many of the applications that we have, and as we use more and more data into them, how do we prevent from using AI-generated content, as you alluded to, will become more dominant? AI-generated content to be recycled back into training these models, and how do we prevent from somebody using them maliciously to generate content that push them in a bad direction?
Thanks again. Yeah, thanks again for the great question. So actually, there are lots of effort. Like first of all, there are existing efforts in the community of using generated content for ASR. So surprisingly, on the same table, you have Bovina, you have Shinji, you have lots of people here, but they worked with their teams on like speech cycle, like models where you train TTS system, generate audio, and use it for ASR, and they have been achieving impressive results on this front. So this already in the making. People have been making great progress, not necessarily using the exact same blocks that I'm talking about, but that direction of research is active and successful. The other point about deep fakes and using speech in very bad ways. So actually, this is a very important block that maybe it's my mistake. I should have added to the block about security of models. Again, like, Hangi himself has worked on, can we have representation models and ensure that it's not memorizing some critical information about the user, about the speaker, about the specific sentences. So there are a lot of research in the community that is focused on securing these models and ensuring that user data is secured. And of course, lots of work in machine learning in general, not in speech, in differential privacy and the ability to build systems that are secured and kind of immune, not fully immune, but we try to make them immune against attacks. So again, this is a very wide area of researchers, not only for representation models, but for even supervised models as well. Any models that are being served, we need to build models for that. And if you take one step up, I know that you're interested in this area as well, which is around ethical use of AI. And like, how can we build ethical guidelines for AI at large? I think this is a very big, important question that we need to think about, not just as researchers, but also with our leaders in the kind of big organizations at the policy level. How can we kind of bridge the gap between the policy expectations and the existing techniques on the ground, and how can we, start incrementally reaching the same kind of high expectations of the policymakers in this area of protecting user privacy? Again, I was presenting like maybe a more other end of the spectrum of saying, like, what, we have everything on the edge, everything is at the user's personal devices. I'm not sending anything back. So at least this also helps a little bit with that. But to achieve this, it requires kind of concerted effort of the entire community to achieve.
Yeah, I was thinking more, think about spam in email, for example. This cat and mouse play. Are we going to see the same thing, as, pre-trained models become the more dominant way of doing language technology in general?
Yeah. Yeah. Thanks again for the question.
We have a question there in the middle.
Yeah, thank you very much for your presentation. I really enjoyed it. I'm curious about what you think of whether AI-generated content is going to replace human-generated content, or whether it will supplement or add value to human-generated content.
Thanks for that great question. Actually, I was discussing that 2 days ago when I was chatting about this particular idea. So, for example, if you need to have a philosophical discussion about a specific topic, so I wouldn't imagine that ChatGPT or any other technique, unless trained on a philosophy, if you need to have, for example, a discussion about Stoicism, you cannot have a ChatGPT to generate something about Stoicism unless it was trained on a lot of books about Stoicism. So it will not come up with that concept. It will not come up with that philosophy and have a kind of enriching and very nice discussion about that particular subject. So these models are not generators of knowledge. They are consumers of knowledge. So we as humans, I hope, will still be the generators of knowledge. We are the ones who are coming up with philosophies. We are coming with new ideas. So what I believe is reasonable. Again, I'm not good at predicting the future, as many of us. I think all of us are not good at predicting the future. But it would be something that's more collaborative, where it will kind of fill in the gaps. Like, rather than, if I want to write a paper, rather than writing it in 4 days, I will write it in 2 days. If I'm writing a book, rather than finishing a new book, writing a book for a writer in a year, he or she will write a book every 2 months. So I think this is where there is back and forth. And I think the challenge would be how to build these very engaging and expressive kind of user interfaces that would allow people to effectively interact with AI power of consuming knowledge. Again, like, rather than doing research in libraries, collect tons of books, and to search and digest lots of knowledge into coherent pieces, you can do that very quickly. And then as a human, I can work with that. Again, the challenge here, both in the AI, of course, building these systems, but also I believe for researchers in human-computer interaction of building these effective interfaces for AI.
Thank you. So it sounds like AI. Okay, as you said, AI doesn't generate new knowledge, but it can help humans to maybe put together knowledge in a way that he or she has not yet considered. That reminds me of a talk that I heard on translation. What do machines replace? Is machine translation going to replace human translator? Like the presenters said that the it will the computers will not replace humans, but rather the computers will help the human translator to do his or her job better.
So yeah, aligned with that, I think it will definitely impact lots of jobs, of course. It just depends on the percentage of human touch on that job. Like, if my job is just, for example, get bunch of graphs, like, people in the, like, say, news industry, like if you pass to me a bunch of numbers and my role is to just write these numbers into coherent text, yes, it's a role of people doing that, but this pretty much could be replaced using AI, and it's in the danger of being replaced. So, but if you need to interpret and say, like, what is the implications of these numbers? For example, you have a bunch of graphs about, like, the financial or economical situation of different countries, how to make inferences about the future. I think this is something that is not necessarily is a capability that AI systems are able to do it. Of course, AI can generate a bunch of things, but like how credible these predictions are is a completely different discussion.
Thank you.
Thanks so much.
Okay. Any question from the audience?
Thanks a lot for a very interesting talk. So are we missing in this framework the other RL, the reinforcement learning idea? So especially if we're talking privacy preserving systems, so you would assume an intelligent system would have situational awareness, where as a consumer I'm interacting, and then completely unsupervised probably would work, but would take a lot longer. While if you have like reinforcement cues from the user, where, for example, the system would learn from habits or kind of continuous conversation, that I would think would make learning easier and possibly faster.
Yes, thanks again for two things. First of all, you reminded me that I've overloaded the symbol RL because I meant representation learning, which also, of course, in that specific setup is also, you can use the other RL, which is reinforcement learning. So thanks for that, for clarifying that. So we are talking about both the representation learning that utilizes reinforcement learning. In the setup of, like, you can think of like the idea of like ambient intelligence. Like, you have systems at home, and these systems are collecting information, again, in privacy preserving way, and learning and interacting, learning from interactions and learning from just listening. So what I was talking about is learning by just listening, not necessarily by interaction. What you are adding to this, which is another amazing dimension, is learning by interaction. So we are combining together just like the passive learning by like representation learning, passively listening or passively seeing what's happening and learning from that, but also learning from interactions, which will add to the richness of experiences that could be built in this intelligent, IoT systems that I believe like will be everywhere in our houses in the next 10 years. I think it's up to us as technologists in this field of, like, to build these systems in the right way, to be fully privacy preserving. How can we have these edge devices adapted for training? All these edge devices was built, of course, they are now like very powerful, but we are all thinking about inference on these devices. How can we think about doing training on these devices? How can we do training on heavily quantized models on the edge devices? So it again opens up a new field and lots of other ideas that could be done in this area. Thanks.
Abdul, thanks for a very nice talk. I had a question about, like, some of the representational issues. Is anybody exploring the idea of, like, the representation changing as you process an utterance? I'll tell you what I'm thinking about. When I listen to somebody with a different accent, like, it takes me maybe a few words, maybe a couple sentences, and then I entrain to that person. And then I don't have as much difficulty listening to them as I did the first time they said something. So for me as a human, if you gave me an utterance from that person and you computed my error rate, whether or not I had heard other sentences from him makes a difference. But when we evaluate our system, we scramble the order of the test sentences. It doesn't matter. We get the same result. But I have a feeling that good representation should change even as you're processing the input. Is anyone thinking about it? Is there any work in that space?
So first of all, thanks for reminding me of one of my kind of like big problems. Like for example, if you listen to like, I guess you have already noticed that I have a problem mixing the P and the B because again, my mother tongue doesn't have the P. So again, like after listening to like couple minutes of my speech, you will realize automatically that I'm mixing them up in a very torturing way for the listeners. So yeah, how to adapt to this? So definitely part of it would have to do with the lifelong learning. We did not explicitly target that particular aspect of um, pronunciation variations or style. You have a person like some people might tend to have certain stresses on some specific words when they speak. That's not necessarily common in the speakers of this language, for example. So there are multiple variations. So at the moment, like for the work that I talked about in continual learning, we did not do adaptation on specific pronunciation or stresses in particular, but rather having like again, like just like doing adaptation on that speaker as we go, but we did not spend enough effort to diagnose what exactly the delta that was captured by that adaptation, which is another fascinating area of thinking about these memories. So if I can have a memory of a specific speaker and then how I'm adapting in that memory, I think this is something that in an explainable way that like after we learn it, we need to understand what happened. We don't have something like that, but our like the system that I was describing, continual deliberate continual and continual learning is doing a form of better speaker adaptation. We get slight gains, but it is again, it's a wide open area. And one reason we had that is actually one reason we believe that um, is like as humans, we gain a ton by adapting to humans, especially for in noisy conditions. If I listen to you before, I can easily adapt to the way that you speak and I speak and so on. So definitely there is a big gold mine of like good research in this area, and hopefully this data set can make some contribution to that direction. Thanks. Ian.
I wish we can have more discussion, but we have to close the session on time. So let's thank our speaker again for the excellent talk. Thank you.
We will have a couple of minutes for update for what's going to happen today. So if you